Hello everyone. In the previous session, we have understood on how we attain this particular formula for entropy. And we also have understood the different steps that are involved in the whole process of selecting the right feature split for the set of feature splits that we are trying to evaluate. So we basically look at calculating the entropy at every individual node, be it a root node or be it a sub node or a decision node, whatever the node it is. You look at computing the entropy value specific to that particular node, and also further look at computing what you call as weighted average entropy for every individual feature split. Like that is, you take the weights into account for every individual subnode. Finally, look at arriving at one specific value that determines the overall impurity or overall homogeneity that you have for that specific feature split. Okay. So now let's look at considering this particular example that we already have dealt with, when we essentially have understood what could be the right feature split by computing or calculating the weighted gene impurity values. That is for credit rating, for credit card, as well as for income group feature splits. We evaluated all these three feature splits. We have understood that we are selecting depth to be 1 always. And that's why we are observing leaf nodes here. These two different nodes cannot be decision nodes. This obviously cannot be a decision node. This also cannot be a decision node because we have kept the depth of this particular decision tree as 1. And as you look at this particular data, we clearly understand that the Gini impurity that we have computed at this particular root node was 0.5, which was a maximum value, since there are exactly the same number of observations with positive as well as negative labels. Likewise, if you are computing the entropy value will always result in 1 for this particular non-homogeneous node, because there are equal number of cases, positive cases as well as negative cases again. When you expand this particular formula for entropy, that is P sub 1 log P sub 1 to the base 2 minus P sub 2 log P sub 2 to the base 2. So P1 here is going to be a value of a value of 0.5. P2 again is going to be a value of 0.5. That is 8 out of 16 is going to always result in 0.5 values for both these positive as well as negative data points. So if you plug in these values, minus 0.5 multiplied by log 1 by 2 to the base 2 minus 1 by 2 is nothing but 0.5 again. 0.5 multiplied by log 1 by 2 to the base 2. So this results in a value of 1. This does indicate that the entropy value that you attain for a non-homogeneous node is going to be maximum in this case. So this is for evaluating credit rating as a whole. So the very first step involves finding entropy values at every individual node. At root node, the entropy value that we have calculated is 1. Likewise, we also calculate the entropy value at subnode S1. This is going to be like what? The P sub 1 value is going to be 0.27. P sub 2 is going to be 0.73. So now you plug in these values in the same formula here. That's going to turn out to minus 0.27 multiplied by log 0.27 minus 0.73 multiplied by log 0.73. Both these logs are having base of 2. And now when you try to compute this value, it results in a value of 0.84. So this here is going to be 0.84. Similarly, if you are computing entropy value at subnode S2, this here is going to be, the P sub 1 value is going to be 1 and P sub 2 is going to be 0. The probability that you pick any one of these points at random, it being a negative, is going to be 0 because there are none of the data points that have negative labels here. And the probability that it belongs to class positive is going to be 1 because all of these are positive here. Just plug in these values. Minus 1 log 1 minus 0 multiplied by log 0. So anything multiplied by log 0 is going to give a value of log 0. Log 1 is 0 and hence 0 minus 0 is going to result in a resultant value of 0. The entropy that we have calculated at subnode S2 is going to be 0. This itself is indicating that this node is a homogeneous node. That is, all the data points are either positive or negative in this case. So a non-homogeneous node will have a maximal value of 1. A homogeneous node will have a minimal value of 0. That's what is a property that we have understood in the previous session also. Now we calculate something called weighted average entropy value. So we know the individual weights here. So there are 11 observations in this subnode S1 out of total 16 that are present in root node. In subnode S2, we have total 5 observations out of 16 that we have in root node. So now since you have these weights that are computed, so you just multiply these individual weights with the respective entropy values that we have computed. So that's going to result in a value of 0.58. So the weighted entropy for this particular credit rating feature split turns out to have a value of 0.58. So we clearly understand that this is quite different from the entropy value that we have calculated at root node. So root node, as we can understand, is a non-homogeneous node. So 1 minus, that is the entropy value that we observe at root node, minus the weighted entropy that we have calculated for feature split is going to result in a resultant value of 0.42. So this 0.42 is nothing but the information gain over what we observe at root node. So at root node, it's complete non-homogeneity. But once we have attained this feature split, we are observing some homogeneity. So what is the information that we have gained by doing this feature split is 0.42. So we attain a weighted entropy value of 0.58. This is the impurity value. And the gain that we observe is 1 minus 0.58. The resultant value here is called as information gain. So likewise, we calculate what we call as weighted entropy for each feature split. We also calculate what the information gain is for that particular feature split. So we just take the difference in between the entropy value at the root node versus the weighted entropy value that we must have computed for that particular feature split. So the next iteration, we are going to consider income group here. So now there are 3 different subnodes that we are supposed to evaluate: subnode S1, subnode S2, and subnode S3. As we can clearly understand, entropy value at root node here is going to be 1 since it's non-homogeneous in nature. The individual weights are 8 by 16, 3 by 16, as well as 5 by 16 here. Now we compute the individual entropy values at every single node. So E sub S1 is going to be nothing but the probability of it being a positive label is going to be 0.12. The probability of a randomly picked up point is going to be a negative label is 0.88. Now you plug in these values here, which turns out to be minus 0.12 multiplied by log 0.12 to the base 2 minus 0.88 log 0.88 to the base 2. So this turns out to have a value of 0.53. So this is going to be 0.53. Likewise, this here is going to be entropy at subnode S2 is going to be a value of 0.91. Entropy at subnode S3 is going to have a value of 0 since all the data points are positive in this particular case. This is a perfect homogeneous node. And obviously P sub 1 is going to be 1 and P sub 2 is going to be 0. Minus 1 log 1 minus 0 is going to result in a value of 0 always. So the entropy value here also indicates that there is little more homogeneity that you are observing, right? Or little less homogeneity to be more precise when compared to the earlier subnode here. Okay. So whatever the case it is, since we have computed the individual entropy values at every node, you multiply these entropy values with the respective weights that we have deduced and then add all of these multiplicative terms so as to attain what could be the weighted entropy value. As we can clearly understand, the entropy at root node is 1 minus the weighted entropy that you have computed for income group split is going to be 0.43. The resultant information gain here is 0.57. Now I am tabulating all these results. For credit card feature split, I have not actually computed the weighted entropy at all. I'm leaving that as an exercise to you. As we have clearly understood in one of our earlier lectures, we had this particular problem of non-homogeneity even in its subnodes for credit card feature split. We observed 50% defaults and 50% non-defaults in every single node, including the root node. So there is no information gain at all. So you're not at all improving the homogeneity in its subnodes, and the information gain that you might compute might result in a value of 0. And hence I have straight away put this particular value of information gain as 0 and entropy for the feature split of credit card as 1 here. And the Gini impurity, the weighted Gini impurity that we have calculated for credit card feature split was 0.5, which was a maximal value. On the same lines, the maximum possible entropy value will be 1, and hence we have used this particular value 1 in this particular tabular column. Similarly, information gain 1 minus 1 will always result in a value of 0 since entropy at root node is 1. And the weighted entropy that you must have calculated also will arrive at 1, since your subnodes also are again non-homogeneous in nature. So we clearly understand the income group is the one that has got the least possible impurity value and the maximum possible information gain. So whichever feature split produces a least possible impurity value and a maximal possible information gain is the one that we need to finalize. So we have finalized income group feature split over all the other feature splits that we have evaluated for the reasons that we are currently observing. For a lower impurity, or for a lower weighted entropy value that we have computed, or for a higher information gain that that particular feature split has attained. Okay, I believe we have thoroughly understood on how we mathematically understand what is the right feature split using both the approaches. Approach 1 using Gini impurity calculations, approach 2 using entropy calculations. Okay, that's all in this particular session, and thanks for watching.